Hey everyone! In today's episode I'm talking to Hamidreza Siampour, and we're going to be discussing an architecture that he built for a broken-symmetry slow light waveguide. Now, what this architecture deals with is how you're able to take emitting photons and direct them in a waveguide. It's broken symmetry, so that means they would either go in one direction or another, depending on polarization in this case. I'm going to let Hamidreza explain that himself, so let's jump into the discussion. So, hi Hamidreza, thank you for joining today.
Hi, and thank you for inviting me.
So, we're going to talk about your paper that you published that I'm also sharing on the screen. It's called Observation of Large Spontaneous Emission Rate Enhancement of Quantum Dots in Broken Symmetry Slow Light Waveguide. Now, there's quite a mouthful to break down. I figured if we start talking about waveguides in general, given that we will be focusing on an architecture for that, would you mind describing what waveguides are in general, and then slow light waveguides in particular?
Yeah, very good question. So, start with waveguides. They consider like two physical objects. So typically, when we have two physical objects, like it can be two, for example, electrons. It can be two atoms that are radiating photons. It can be even two mass, like they have like gravitational forces. So when you think about two physical objects, this interaction usually associated with kind of proximity, distance. So when you increase the distance, you normally experience a decay in the interaction, so you lose the interactions. At some specific distance, there might be no interaction at all. For example, when you speak to some person, so if the distance is really increased by like 1 kilometer, so you cannot communicate anymore. Mm-hmm. So to that sense, actually now, if somehow we could manage to make a channel that you could share for example, you can talk through this channel, so you don't need to worry about the distance anymore from yourself, from your side, or that specific physical object and the other physical object. But what you need to worry about is how to effectively put the information in that channel, and that you don't lose any information. And this channel, you trust this channel, can mediate the interaction between you or your object and the other object in the other side. So now the distance is not any more important, but what is important is how to effectively transfer information. For example, if it is radiating atoms, how to effectively transfer photons to this shared channel, shared radiation mode. And then this channel actually now is responsible to carry the information and send it through. And hopefully at the end also you need to effectively receive those information, all of those information in receipt. So once we are talking about photons, transmitting photons, which is kind of a electromagnetic wave, so then we call this shared radiation mode waveguide. So waveguide actually now is mediating our interaction between two atoms, one, for example, transmitter, one receiver, and these photons that are kind of electromagnetic waves can couple through and propagate through these optical waveguides and maintain the interaction even beyond proximity. So one of the actually useful application of this, if you go to like very fundamental, so when we think about matter is kind of like constitute of several millions of atoms, and these atoms need to be very close to each other to make, for example, covalent bond. So, but now if there is possibility to maintain the interaction through this shared mode, so we don't need to actually think about having these atoms very close to each other, so they can be far from each other, and then we just need to effectively couple them through the waveguide, this shared radiation mode, and then now at top you will manage that, for example, which atom should communicate with which atom, and then you can design new material that probably not exist in nature, and You can even change your material by changing the which atom now has to talk to which atom. So you can also change. So you can go beyond the common or natural material. We can design new quantum materials. This is like at the very fundamental level. But now we can also think about even motivate these photons that typically propagate very fast with the speed of light, and the reason that we use actually photons to carry information because they don't interact. They don't have actually enough time to interact with medium, so that's why whatever you give them, you don't lose them because they don't interact with other material, with other atoms. Therefore, the information will be maintained from the beginning to the end to the destination. So sometimes actually in the beginning of the interaction, for example, once atoms need to couple to the waveguide, and at the distance in the other side, when they want to couple to or give the information to the second atom, we need such kind of interaction there. Also, they don't interact typically, but on that situation, we need to slow down the speed by some additional time for photons to be able to interact with atoms, and for that reason, actually, we came to this concept of a slow light. So
okay, so the slow light aspect of this particular waveguide is not necessarily to get the waveguide itself to function the way you want it to, but rather as a desirable feature of the architecture because it's useful in the applications of it.
Yeah, the waveguide itself is to mediate the interaction between distant atoms, but when there is an interaction between emitter or radiating atoms, in our case quantum dots, that they are like semiconductor nanoparticles, that they work very similar to atoms, so they have discrete energy levels. Also, they are not exactly atom, but they act like atom. So they have ground state and excited state like atom. We can model them like a 2D, two-level system, and we have them embedded inside waveguide, and at some specific points, they have to kind of interact with waveguides. But since photons are very fast, they don't usually interact with any material unless we force them to interact. And one way to force them to interact is to slow down the speed of those photons by using the geometry in the waveguide. For example, using photonic crystals, we are able to reduce the group velocity, which is actually responsible to define the speed of wave while propagating through the wave.
Mm-hmm. Okay, so maybe to make it even more concrete now with the architecture that you're proposing in the paper, I'm sharing on the screen now the image. I hope you can see it of the architecture. So the waveguide itself would be considered, I guess, the entire structure here on the top figure. That's correct, right?
Yeah, this is a kind of a prototype of our device. So yeah, you can see in the center you have your radiating atoms. These radiating atoms, first we need to excite them, meaning that if we consider a two-level system, so now your electrons are in ground state and we need to promote these electrons to excited state. For that we use excitation power. Here we use green arrow, as you see in the center. This is like.
Is that normally a light source, or what kind of excitation?
Yeah, this is a light. This is a laser source we use to excite our quantum dots. In this case, it's not a really green laser. In this case, it's a near infrared laser about 808 nanometer. That's the wavelength. But this wavelength, this laser energy need to be larger than the band gap of the our two-level system. So, so energy converted to electrons is large enough to promote electrons from ground state to excited state. So that's actually the function of this pump, what we call them pump laser or excitation laser. So then once your atoms promoted to excited state, then after a while that we don't know, is completely spontaneous, they will get back to ground state, but they release this energy as a form of photon.
Mm-hmm.
So we don't know how long does it take. It can be immediately once they go up, it can be down. It can be after, for example, 1 picosecond. It can be after 1 nanosecond. It can be like after 1 day. So, but in reality, what we do actually in the measurement, we try to promote this atom, for example, 1 million times, and on average, we see after 1 million times on average how long does it take. For example, in quantum dots that we are talking about, on average after 1 nanosecond, they will release a photon and then relax, coming back from excited state to ground state. So that's the typical lifetime or decay time of these atoms after excitation. How long does it take to relax? We call them spontaneous emission. But also it's spontaneous. It doesn't mean that we don't have any control. Actually, it's spontaneous, but it's not an intrinsic characteristics of this radiated atom. Environment can change it, and we can control the environment, and our environment now is waveguide. So we work on design of waveguide in a way that we can ramp up the this relaxation rate. So we can generate photons by a higher rate. So increase the rate of generation. So, and if we increase the rate of generation, meaning that we have now more capacity to send more information. It seems like you are talking with a higher speed, so you can generate more words, for example, per second. So it looks like that. So if you could increase the this generation rate, for example, by a factor of 100, so it looks like you increased your bandwidth by a factor of 100. It's kind of like that.
Right.
So typically it's 1 nanosecond, but in this waveguides we bring it down to about 60 picosecond. So which was kind of a record for quantum dots in waveguide. So it means that the design and fabrication went very well. So now instead of waiting, for example, for 1 nanosecond, so we just need to wait, for example, 60 picosecond to get 1 photon. So that's actually the functionality of this slow light, because slow light allows us to kind of increase the interaction between photons and emitter, and therefore by enhancing the interaction, so now we provide larger density of states for atoms to be able to relax, and therefore they generate more photons for us.
Okay, is that intrinsic? So, okay, two things. I guess first of all, this is very related to the Purcell factor, right? Or Purcell enhancement. I guess that's what you're describing with the emission rates of the quantum dots and the fact that we can shorten the lifespan, if you will, of that to increase the bandwidth of our system. The last point you mentioned, I didn't quite understand. So you said that if we're using a slow light waveguide, in this case, you're increasing the interaction between, let's say, your pumping laser and the quantum dots embedded in this material, and hence you're exciting, let's say, higher density of particles more particles per time unit. My understanding is that in order to increase the bandwidth, it's not so much a function of how many atoms you excite to begin with, but rather what the, let's say, half-life is of those atoms. Am I thinking about that wrong? Because if it is intrinsically related to the half-life of the atoms, then I wouldn't expect that the pumping laser has any effect on let's say, the Purcell enhancement in this kind of case?
It's good that you mentioned Purcell. So Purcell actually was the first physicist to discover that this spontaneous emission rate is not an intrinsic characteristics of atom. So if we change the environment, it can be changed. His suggestion was to use cavity, and inside the cavity, for example, if you put two mirrors, and then now atoms inside of these two mirrors, so photons cannot leave easily. So these atoms see these photons if we design it properly. So located inside this, it can go through a lot of round trips inside of this cavity between these two mirrors, and based on his calculation, he obtained that this emission rate will be enhanced by a factor. Now we call it Purcell factor, which is related to the Q factor of this cavity, meaning that this Q factor is very related to the number of round trips of these photons, how many times these photons, for example, stay or go through this round trip before leaving the cavity, and then divided by volume. So if the cavity, if you reduce the volume, so obviously the interaction will be increased. So because now we are closer, if we bring this mirror very close. So this also gives us some confinement of light. So that is for cavity. But now, similar to cavity, we could extend this idea to waveguide. In waveguide, instead of having Q factor, we have group velocity. So what happens inside the cavity, actually, your photons does not leave cavity if the Q factor is very high, and it kind of slow down the interaction, slow down the speed, because they have to stop inside the cavity for a while before leaving, and then through this round trip they can see atoms more and more, and then they have more possibility to interact. So other way, here in waveguide, we don't have these two mirrors, but instead we just reduce the speed, and then, for example, they have 20 like fold delay, for example, 20 times more time to be able to propagate inside the cavity, and therefore by this factor we could expect to have larger interaction. Also, we could also gain, instead of volume, now we have cross section of this waveguide, which is in nanoscale. So this reducing the size of the waveguide, that now we have this, as you see here, there is a line defect inside the photonic crystal, and this line defect actually define our waveguide. So when we reduce the line defect, so this line defect actually determine the size, the area, the effective area of the waveguide by reducing that, and by increasing the group velocity, by reducing the group velocity, meaning that we reduce the speed of light, we are effectively increasing the Purcell. Now Purcell, instead of saying Q over V, quality factor of cavity divided by volume, now we are saying the group index, because instead of saying Q factor, now we say group index, and group index is related to the inverse of group velocity. So reducing the speed by a factor of 100, meaning that we have 100 group index, so group index of 100. So now group index divided by area here determines your Purcell factor. So by increasing the group index or reducing the group velocity, and by reducing the area, we are effectively enhance the emission rate because of the Purcell.
Okay.
And yeah.
So I guess the Purcell enhancement then describes rather, let's say, the emission rate increase of a system?
Yes.
of the system in its entirety, let's say, really the emission rate increase, and not, let's say, the amount of time necessary for that system to return to its ground state. I think my original question and what had me slightly confused before was I was relating the Purcell factor to the time it takes for the system to get back to its, let's say, unexcited ground state after we cut off the laser. I was thinking about this from an, let's say, bandwidth perspective if you're sending information, and I thought it was relevant for, let's say, the lifetime of the system to be as short as possible after you turn off the laser. Because if you have, let's say, some form of communication where your laser is, turning on and off, then you would need not only to be able to emit a large number of photons when the laser is on, but it would also need to, let's say, revert back to the base state very quickly after you turn it off. But I'm not sure if I'm thinking about that in the right way, or maybe I'm mistaken there.
Actually, both of them are related, because once you turn off the laser, so now, and this is what we do actually, because we use pulse laser. And by pulse laser, this means that you have on and off, on and off. It is on for a while and then off. And then once it is off, you see a decay, exponential decay in our measurement, which meaning that it takes a while for this excited atom to be grounded. And this time, if it is Purcell enhanced, for example, it's about 60 picosecond. And the time that laser is on actually is much shorter than this lifetime. And therefore, the laser always beat the lifetime, and it has to be, because it has to be on and quickly off, and then we wait how long does it take for atom to be reduced. And if we reduce this lifetime, we can already increase the bandwidth as well. But at the same time, when we reduce the lifetime, also this means that we are generating photons faster, meaning that if we use these photons later, this single photon source, as a source that can generate information, this meaning that we are generating more information per second, which is related to larger bandwidths.
Okay, no, but then I think we understand each other. Good. I think the second part that I would like to ask about is on this architecture. This is also, let's say, a broken-symmetry architecture, right? So can you explain, with the help of the figure here, what that means? So what this broken-symmetry concept, what it means from the architectural perspective, but then also why there's a use case for these kinds of architectures.
So when we excite atoms, these photons, these atoms, as I said, after a while they emit photons, and these photons has polarization. So it can be right-hand polarization, or it can be left-hand polarization. So it depends on the right and or left, and or we could say like right hand or the spin up, for example, or left hand spin down. So we can associate this polarization to spin state as well. So these photons actually have information, and this information is spin, is polarization. So it's kind of like 50%. 50% might be left hand or spin down, as I showed here, for example, sigma plus, sigma minus. 50% of time is spin minus, spin down or spin up. So this has to do with polarization of photons. Now we designed waveguide in a way that not only interact with atoms, but also enable us to extract this information from photons. So photons now carry information, and this information is a spin. So it's polarization. And this is actually the way that we encode information, similar to electronics, that, for example, we have transistor on and off, meaning 0 and 1 in digital bits. Now we create our quantum information by using this spin, saying spin up or spin down is kind of 0 and 1, but now since we don't know whether it is 0 and 1, it can be simultaneously 0 and 1, because uh, until we measure these photons. Once this atom emit photon, it has actually spun at the same time. It has a spin up and a spin down until we measure it. So we make use of this superposition of a spin up and a spin down to encode our quantum information. I would like to separate those spins and entangle them with the direction of propagation. So this waveguide is symmetry broken, meaning that now photons that couple to the waveguide, they don't necessarily couple to the left or right side of the waveguide with the same probability. So we managed to design in a way that, for example, a spin up only couple to the left side of the waveguide and a spin down only couple to the right side of the waveguide. So by this way, we kind of entangle the polarization, these spin properties of photons, to the direction of propagation while they couple to the waveguide. There's kind of a spin path entanglement, what we did in this waveguide. So not only increase the generation of photons, but also map the information that coming from photons, this spin information that will be used for quantum processing, to the direction of waveguide. So map the information from photons to the matter. So we designed the environment in a way that we could map the information from photons to the material state. In this case is the direction of propagation. So it's, in technical term, scientists say spin photon, spin momentum locking of light. So the momentum of light locked to the spin, to the polarization. So and this has been done with waveguide. So waveguide now determine whether photons should go to the left or whether it has to be blocked going to the left, or it should go to the right. It's working like a diode in electronics. In electronics, for example, electrons can go only in the one direction of diode, but in the other direction, diode will block them. We have kind of like similar things now in optics. So optical waves can only go in one direction, and the other direction they will be blocked, because the polarization content of this optical mode that are carrying photons are designed in a way that only allows specific polarization to pass through. So that's actually the reason that we break the symmetry. Now, if it was symmetric, so 50% of photon go to the left, 50% go to the right, and now they are broken. We broke the symmetry in a way that about 100% of photons that are sacrally polarized in the left-handed only go, for example, to the left or to the right, vice versa.
Mm-hmm. Okay, so I have two follow-up questions on this. The first one would be, we're saying that we can control the polarization of the light coming in the pump laser, and that's fine. The first question I would have is, with the interaction between the photon and the initial quantum dots, my understanding originally was you would have some photon coming in, it would excite a quantum dot here, the quantum dot would then get a polarization which is pretty much 50-50 in a symmetrical waveguide. How is it different now? So this is my first question. How is it different now in this broken symmetry waveguide? How are you able to transfer the polarization from the light to the first quantum dot? So fine, we have some way of having this waveguide propagate, let's say, quantum dots where the spin is in one particular direction to the left and the other to the right. But how do we actually transfer the polarization from the light to the first excited quantum dot when it seems like the only thing we do is pump the energy of it to an additional energy state? What is it that I'm missing in that equation? How can we control, based on the polarization of the light, where the first quantum dot ends up in the excitation?
Yeah, when we excite the quantum dot, at this point, we don't transfer any polarization to quantum dot. So we have like a pump laser, and we just excite quantum dots. So now after relaxation, so you have photons, and this photon can be left-handed or right-handed. Until now, we don't have any control. So,
okay.
but after that, these photons is going to couple to the waveguide, and now depends on its polarization, we determine whether it has to go to the left or to the right side of the waveguide. This is the point actually that we have control, and we can manipulate the information based on the polarization of photons, but not the excitation laser. Excitation laser is fixed.
Okay, then I understand. Is there, so a slight detour and follow-up question, is there a way to actually control the polarization of the quantum dots when you initially excite them? Like, let's say you wanted to use this kind of system as a way to control, let's say, whether or not you send energy to the left or to the right. If you could control the polarization of the initial excitation, then I guess this would be an architecture to do that. Is that possible, or is that simply not physically, feasible at all?
So now if this, for example, photons that are coupled to quantum dots, number one, so is going to excite another quantum dot that is, for example, exists in the same waveguide, and they are sharing the same optical mode, they can talk to each other. So now if it is, for example, a left-handed sacral polarization photon, now coupled to the waveguide will determine the direction. Now there is, for example, is coupled to the right side, right direction. Now in the right direction there is another atom. This atom can see this photon coming, and if they are very well coupled to the waveguide, we use the term cooperativity. If the coupling efficiency of atom, radiating atom, and waveguide is very large, meaning that, for example, we don't lose any photons, all of the photons just couple to waveguide and they don't go to free space. So in this case we have like very large cooperativity. Nowadays we can think about like cooperativity at about 60, which is like coupling efficiency of 99%, meaning that 99% of photons couple to waveguide. So in this case, these photons couple to the waveguide, and then these photons coming from the quantum dot number one, and has polarization, and mode has polarization content, so that's why it can determine the direction. Now it can propagate and reach quantum dot number two, but now this quantum dot number two will be excited by a photon that we know has a specific information, has a specific polarization. And this is the place that actually we can map the information from the coupled photon, from the photons that excite the quantum dot number two. And this is the way actually we can map this information from photons to the next quantum dot. So now the quantum dot that will be excited, the second quantum dot, has this additional polarization information from coupled photon.
Mm-hmm. Okay. Yes. One question on the initial direction being chosen by the first quantum dot that gets excited. How does that assignment work based on the polarization? So you excite the atom, it relaxes again, emits a photon of a given polarization, and this architecture somehow magically, to me at this point, assigns it to propagate either to the left or to the right based on its polarization. Do you have a conceptual explanation for how that works? How can you assign a direction of travel for the photon purely based on what polarization it has?
Oh yeah, very good question. So when we consider for example, optical fibers, so they are very symmetric, usual fibers that we use. So if you couple light, for example, from the middle, so 50% of light go to the left and the right, other 50%, and polarization content of optical mode determine the polarization of those photons that are coupled. But and this is actually, we are talking about micrometer scale area for optical fibers. Okay, But when we reduce this area, this cross section, and make it very small, so now in what happens in optical fibers, you have mainly your fundamental mode has almost only one polarization, which is perpendicular to the axis of waveguide. And polarization actually is nothing but the direction of electric field. So electric field is a vector, and the direction of electric field has been actually used to determine the polarization. We call it polarization, meaning that the direction of electric. So the direction of electric field is perpendicular to the axis of fiber, and it is almost for the usual fibers is like that, and then your energy propagates through the waveguide while the direction of polarization is always perpendicular. And the reason that why it's perpendicular, because the size of optics, the size of waveguide is within like micrometer, few micrometer scale, and wavelengths, which is for example, for communication wavelengths is like about 1.5 micrometer. In our case here is about 0.9 micrometer. So the size of waveguides is much larger than the wavelengths of light. So in that case, the longitudinal component of electric field is almost negligible, and you have only perpendicular electric field component, and that's the major polarization of it. But when you reduce the cross section, reduce the size, since the longitudinal component of the electric field is related to the confinement of the lateral component, so when you reduce the size, so this longitudinal component becomes large, and at one point it can be as large as your lateral component. So now you have two electric components. One is longitudinal along the optical waveguide, and one is lateral, perpendicular. And based on Gauss equation that determines actually or Maxwell equation that determines how these optical waves, optical or electromagnetic waves can propagate through the waveguide, there is like an imaginary term. So this electric field along the waveguide and perpendicular to the waveguide, they are oscillating 90 degrees out of phase. So now we reduce the size, they are always oscillating 90 degrees out of phase. When the waveguide is large, the longitudinal component amplitude is very small, negligible. So we almost say we have only perpendicular. When we reduce the size, now the longitudinal component becomes large. And on then the specific point of the waveguide, these two components, longitudinal and perpendicular, becomes quite similar in amplitude, and in phase they are 90 degrees out of phase. They are oscillating 90 degrees out of phase, and this condition actually naturally formed circular polarization. Circular polarization actually is nothing but having two electric components that has almost the same amplitude but oscillating 90 degrees out of phase. So we naturally make this local condition inside the waveguide, but just reducing the cross section, and in a specific part of the waveguide we make this this circular polarization. And now you have photons that they have also circular polarization, but depends on the sense of circulation. It might be matched with your local circularly polarized light field inside the waveguide, or they might be not matched. They might be orthogonal. They might be opposite. So if they are in the same circulation, in the same sense of circulation, they will be coupled. If they are opposite, I have local polarization inside the waveguide, for example, is right-handed, but my photons is left-handed, they cannot couple. So that's the way actually this spin momentum locking of light, the way that we link momentum or direction of propagation and spin or circular polarization of photons. This is the way that we link these two together. So they will be locked based on the sense of circulation. Now we have natural local polarization inside the optical waveguide because they are nanoscale, they are beyond the diffraction, they are smaller than wavelengths, like sub-wavelengths regime. So it can be done only when we reduce the cross-section in a way that goes like less than wavelengths of the photon. And then we have natural circular polarization. We have photons that are also circularly polarized. If the sense of circulation are similar, they are very well coupled. If they are opposite, they just block the direction of propagation. So that is actually, it has to do with the size of wave.
Okay. I have two follow-up questions on this. I think the most relevant of them would perhaps be how the material is prepared so that this circular polarization actually arises. So I get the point you were saying on the scale. We need to have small enough of a cross-section in this architecture for it to actually get locked into the architecture. As far as getting circular polarization also, because the way I understood it is that you also have a circular polarization of sort in the material of this architecture. How does it come about that is actually circular, that polarization?
So how we know that the material that we use, gallium arsenide, and we made our waveguide from this gallium arsenide platform. So, and gallium arsenide has a specific refractive index, so it does not have actually a specific polarization, but when we introduce waveguide using this material just gives the refractive index from optics point of view. It has a specific refractive index at specific wavelengths. We know that, and we use that data when we design our waveguide. Based on that data, we know how small we can make the cross-section to be able to, for example, make it smaller than wavelengths of photons, because wavelengths of photons inside waveguide compared to free space has like additional factor which will be determined by this refractive index. So if, for example, the wavelengths in free space is 900, so when light goes inside this gallium arsenide, the wavelengths becomes 900 divided by refractive index, and in gallium arsenide refractive index is about 3.5. So you have like 3.5 less wavelengths. So by this factor, we have to also reduce the size of this waveguide. If we are in the center of waveguide, in the center of this line defect, so the polarization is linear, and if your atom is exactly in the middle of the waveguide, the coupling is symmetric. But if you go slightly off center, so this is the place that you have your local circular polarization, and we managed to put these atoms, they can be randomly positioned, or we can also deterministically position this atom exactly on this off center that we have pure circular polarization. And by that trick, those photons that have also circular polarization see this circular polarization, local circular polarization. We call them chiral points. If atoms located in chiral point, which is a natural local circular polarization light field, so photons coupled to this waveguide based on the sense of circulation that they can share with local chiral points.
Hmm. Maybe we can scroll down actually, because I think you have a figure later in the paper here of the chiral points, right? So
Yes.
this one I think illustrates, well, the directionality is what we have here, color coded, and I think that's the quantity you're referring to. Is that right?
Yeah, exactly. So you see the red light and blue light. So they show opposite sense of circulation. For example, +1, you could say the pure circular polarization, which is, for example, right hand, and -1 is a pure circular polarization. And anything in between is just a like combination of this longitudinal and lateral components that might be not necessarily circular because the amplitude now is changing from one position to another position. Those that are like really pure circular, they are red, but which means that the two components of electric field, one along the waveguide and one perpendicular to the waveguide, they have exactly the same amplitude. But those that are not and are in between red and blue, they have like different contribution of lateral and longitudinal electric component. Yeah, and in some specific cases, when it is 0, you have pure linear polarization, which means that you have only one component, which is lateral component, and longitudinal component is almost 0. So if your atoms are located in that position, they don't see any chirality, and they can couple to waveguide regardless of their polarization.
Okay, thank you for that explanation. If we scroll back up again, we can have a look at the structure of this waveguide, the intersection. Let me see if I can zoom in on the paper. I'm thinking specifically about figure D here, because I think the holes in this architecture are, well, the geometry here is quite interesting, right? So it's non-symmetric in a way, meaning that the holes have different sizes here, and then we also have a glide line here in the middle. Could you perhaps explain how you arrived at this particular architecture? Why is this preferential for, well, the objective of directing the light in one of these two directions?
Mm-hmm. So if in a usual architecture, so we have completely up-down symmetry. So if we consider this dashed line as our reference line, so in the case of completely up-down symmetry, everything on top it has to be reflected or mirror image and down. So in that case, we have usual photonic crystal waveguide, what is called W1 waveguide. So we tried that waveguide, and it turns out that we have very small regions of these chiral points. So the place, even though we reduce the size of cross section, but still we have very limited places of these chiral points that we need for interacting with circular polarization. But if we add like additional symmetry to this up-down, and this a little bit more complex symmetry is to add up-down plus translational symmetry. We have a periodicity, if you consider two holes, all of those two holes in a like direction of propagation have a specific distance. So if we move the bottom part of the photonic crystal to the right by a factor of a half factor, like 50% of this periodicity. So now we have a symmetry that is up-down plus translation. So up-down plus translational symmetry, and this is actually, we call it glide line because this is similar the way when we, for example, walk, we always make this uh, up. We always make this mirror image, but at the same time we add some translation to the next image. The way that our feet, for example, go to make this walking happen. It turns out that when we do that and we do simulation, it turns out now we have access to a larger area that we can call chiral. We can make this natural circular polarized light in a larger area, and in particular we also can overlap this chiral area with the position that we have also high electric field intensity, because electric field intensity is position dependent. So we don't get like high electric field intensity in all of these waveguide position. So as you see in the right side of the figure, there is another figure. It's called Purcell factor, so which can be calculated based on the electric field intensity. So this shows actually the electric intensity profile. So ideally, we would like to have our chiral point overlapped with this map, with this Purcell factor map. So which means that now, if we put our atom inside the waveguide, if they can be in a region that we have high Purcell factor, high electric field intensity, they can generate more photons, and at the same time, this position need to be overlapped with the chiral region that you have pure circular polarization light field. So then at the same time we have high generation of photons that can be mapped to the direction of waveguide. So this glide plane or glide line symmetry helps to overlap these two different regions together. So now we have two maps. One is electric field intensity that the high electric field intensity need to be mapped to chiral map, need to be overlapped with the chiral map, where we could have pure circular polarization. So that's the reason that actually we end up using this complex symmetry.
Mm-hmm. Okay, thank you for that good explanation. So we're rolling up on time, but the last question I would ask is there an easy explanation for why we have the holes in this architecture that we have? So we see that both the Purcell factor in this figure and then also the chirality that we saw before seems to be tied to these holes. Do you have a intuitive explanation for why these holes need to be in the architecture, and what would happen if we simply remove them?
Yeah, if we, for example, don't use any holes, just make a like rectangular waveguide, right? Mm-hmm. If you just use a rectangular waveguide, still we can generate this pure circular polarization, and if we put our atoms slightly off center, we experience this spin momentum locking of light, this spin photon entanglement. But the problem is we lose Purcell factor, because the way that we get this Purcell factor is because of group velocity, and group velocity is nothing but the slope of this figure. The middle figure shows band structure. So this photonic crystal similar to atoms that have band structure, and photonic crystal also kind of mimicking material, the periodic structures in material to make this band structure. And by playing with different symmetry, we are able to engineer band structure in a way that in some places you can have large group velocity, and group velocity here group in a large group velocity. Group velocity here, a small group velocity or large group index. And group velocity here is the slope of the band structure. So as you see, if you go to the place in the middle that shows the slow light, there are places that the slope is almost vanishing, meaning that like the parallel to the x-axis. So this is the place that actually we see a very large slowdown factor. This group index is slowdown factor, meaning that your group index is your group velocity is almost vanishing. So the speed of photons now very slow, and this can be done only if we could use this periodic structure of nanoholes. It can be circular nanoholes, it can be rectangular nanoholes, but it has to be kind of periodic structure in a way that I can engineer this band structure and make it in a way that, for example, some places I have a slope that is vanishing, and then I get my large slowdown factor.
Mm-hmm. Okay, I understand. I'm going to let you go now, but before I do, I just want to ask if there were any key takeaways from this paper that led to, let's say, well, new research being conducted, or any sort of takeaways you would like the audience that have listened to this to take away as sort of a main result of your paper.
Yeah, in this paper actually we shows that quantum information, in particular spin qubits, can be mapped, information can be mapped to material properties. In this case, for example, in the direction of waveguide, and this can be done completely quantum mechanically, all the way down to a level of single photons. And now if we use this single photon as our flying qubit, you have this now opportunity to determine their direction, meaning that you can manipulate these flying qubits based on their polarization, their spin qubits. So this is the open new avenues for processing information at single photon level, or that carrying quantum information. So this is kind of like a physical implementation of quantum information processing in the very beginning. So now it's only one atom. We made it for one atom, but ideally in the future we would like to scale up, put the second atom, a third atom, and hopefully have an ensemble of atoms that are coupled to the waveguide, and each of them we have control that whether how they can interact with each other. For example, if atom number 2 is positioned in the right side of the atom number 1, and then you manage to make use of, for example, specific polarization, so only atom number 2, for example, can see atom number 1, but atom number 1 cannot see atom number 2 because the information are unidirectional. And this is the way that we can also think of designing new quantum material and also make use of them for new regime of processing and computation.
Wonderful. Thank you so much for taking the time. We're going to wrap up the discussion here. I just want to really say thank you for presenting it. I think this was a super interesting discussion, so thanks for taking the time.
Thank you very much.